All right, and we're back. This is a continuation, part two of chapter 13, an introduction to landform study. Again, from McKnight's Physical Geography, a Landscape Appreciation, published by Pearson. We finished up with igneous rocks on the last section, and the big takeaway from that was the slower that rocks cool, the longer the minerals have time to coalesce together, and therefore the bigger they are. And the faster it cools, the more glassy it is because the minerals, again, are much smaller. Just to give you an idea, I picked this rock up several years ago. It lays by my phone. It's kind of a paperweight. But this here, as you can see, has a large chunk, get back over here, of feldspar right in the center. Therefore, this rock, it comes from the Colorado Rockies, had a long time to cool. This is one of the few chunks of feldspar I've ever seen that's really this large. And it's in, of course, a piece of granite that is white and pink quartzite. All right, so we're going to continue on here. All right, so now we're to sedimentary rocks. External processes cause rocks to disintegrate. It's called denudation, erosion, weathering, but it brings down the landscape. So we take in mountains erode away, and that sediment turns around and makes its way down to rivers and stuff, and ends up eventually back out into the ocean as sediment. For the most part, sand. But there's a lot of sediment in these layers. They get compressed and compacted. So the material is transported by water as sediment. Over long periods, large amounts of sediment build to large thicknesses and exert an enormous pressure that causes particles in the sediment to interlock. So as you build these layers, you get heavier and heavier and heavier and heavier and heavier, and it's compressing all that. It exerts enormous pressure that causes particles of sediment to interlock, and then chemical cementation takes place. Well, where do we get chemical cementation? Well, there's a couple things. First of all, we have carbon dioxide. We have everything that's in our atmosphere. It gets absorbed by water. In fact, the oceans are often called a carbon dump. But there's also lots of microscopic creatures in the ocean, and they excrete. And those excretions end up being deposited into the sediment in the bottom of the ocean and acts kind of like a glue, right? Which forms sedimentary rocks. Strata, horizontal layers of sedimentary rocks, sometimes tilted into vertical by Earth's processes. And that just comes to tectonics and faulting and folding. But we've seen strata. We went over that in the last chapter 12, those horizontal layers I was talking about, whether it's soil, but soil, if it's left alone, compacted, compressed, and cemented long enough, becomes rock. Here in Oklahoma, we have a lot of sedimentary rock. We have sandstone. Here's a couple of figures that show you an example of sedimentary rock, and it shows you those horizontal layers here on the left-hand side. We can just see all those little bitty layers in there, and I cannot draw right now, but hey, there we go. All those sedimentary layers, everyone there. And you have more resistant rock, and you have less resistant rock. You have to remember, water, and we're going to get into this into another chapter, but you need to know now, water always takes the path of least resistance. So whatever is more resistant to water is going to last longer than that which is less resistant. If it's less resistant, it's more erodible, right? And here on this right-hand side here, we have, again, you can see some of the feldspar in there, okay? But we have this quartzite, this is sandstone, but you can see these different layers, okay? Those are all horizontal layers. So we have two primary types of sedimentary rocks, detrital or clastic, composed of fragments of pre-existing rocks. So it's chunks of rocks that have been glued together, also known as detrital rocks. Shale is an example of that. Conglomerate, that's the one, we see a lot of shale, but if you're running around on a riverbed, you can find some conglomerate composed of pebble-sized fragments. I actually found a shark's tooth one time inside a conglomerate. I took the conglomerate back to the lab, we did some work, and there's a way to break that conglomerate down, but we did it, and inside was a beautiful shark's tooth. Chemical and organic sedimentary rocks, formed by precipitation of soluble materials or complicated chemical reactions. For instance, limestone and coal, right? And we're going to get more into the limestone later, But yes, it is associated with caves. Coal, of course, associated with bogs, and so on. Organic sedimentary rocks such as coal form from the remains of dead plants and animals. The two primary types of sedimentary rocks are white rocks is limestone, and the dark rock is shale. And here we have this Mount Angelia here in Washington State. And as you can see, it's been tilted upright. That comes from folding and faulting. Okay, folding and faulting. It gets tipped upright. I don't know if any of you have ever been to Dinosaur Monument National Park there on the Colorado-Utah border. A beautiful place. If you ever get a chance, go see it. But it looks like all the dinosaurs that are in the rocks are all running uphill because it's tilted and angled. It's been folded and faulted upward. And our last group of rocks is metamorphic rocks. So you got to remember we had three: igneous, sedimentary, now we're at metamorphic. Metamorphic rocks, rocks that were originally igneous or sedimentary and have been changed by heat and pressure. You take and you push that heat together, or put that pressure on there and add some heat to it, and you warp the chemical actions and you change some mineral components, okay? Causes the cooking of the rocks. Rearranges that crystal structure of the original rocks. Contact metamorphism, rock contacts magma and is rearranged. So it's a rock that was originally, whether it was igneous or not, was created by heat, but then we add heat again. It's kind of like making a sword back in the old days. I don't know if you've ever heard of them folding, but they would fold it 100 times or 200 times, and it just made it stronger and stronger and stronger. Regional metamorphism. Large volumes of rocks are subjected to heat and pressure over long time scales. Maybe not like contact where it's touching magma, but there's enough heat around it that it changes that mineral structure. For instance, limestone becomes marble, sandstone becomes quartzite, and shale becomes slate. Here are some other ones: schist, metamorphic rocks with narrow foliations. You can see these foliations where it's kind of changed that crystal. And why do we have this warp in it here? That's due to folding. The same down here, gneiss, broad-banded foliations. Again, it's been folded. We've got those curves in there. We can also see here the horizontal strata. Okay, there's our different layers. Here is table 13-2, which kind of breaks down everything. Igneous tells you about whether extrusive or intrusive, plutonic and volcanic. We got sedimentary, detrital, and it just gives you names of all the different ones: chert, quartzite, marble, and so on. This is actually a figure. Make sure you take a look at this. It kind of helps you better understand the rock cycle. So we have solar energy, of course, heating everything up, and we have weathering and erosion and deposition. So we get these sediments. The sediments go to the ocean and create sedimentary rock, and then it gets uplifted or finds its way into folding and faulting, and we get metamorphic rocks that have been heated through pressure and heat. And then metamorphic rocks can be then subducted and re-uplifted and turned back into igneous rocks. And as you can see, each one of these is connected to the other. All right, so continental ocean floor. Some of the things you need to know here: sedimentary rocks make up 75% of the continents. By and far, the majority of the rocks that we see are sedimentary. They're the most widespread rocks. Now, don't get me wrong, mountains and stuff, yes, they're very large, but they're localized. We find sedimentary rocks everywhere. The sedimentary cover is not all that thick because it's sediments that were compacted and cemented and then uplifted. The continental crust is created of silicon and aluminum, whereas the ocean floor crust is silicon and magnesium. Ocean lithosphere, we've already said this, so now you've heard it a couple times. That should give you a hint about something. Ocean lithosphere is more dense than continental lithosphere. Again, the continents kind of float, they're more buoyant. Ocean crust can be subducted into this asthenosphere. We're going to get into that in the next chapter when we start talking about divergence and convergence of plate boundaries. Isostasy, recognition of differences between oceanic crust and continental crust, and mantle rebound. Okay, so, and I'm going to try to draw here. So what that means, and we've talked about this before when we've talked about sea level rise, there's a couple of different things. One is adding actual water to the sea, which causes sea level rise. And the other part is this isostasy or rebound. So what it is you've got a continent here, and the continent's edges are pulled up because you got this big ice block on it, okay? And it's pushing down in the middle, causing the corners to warp up. However, as that ice melts, which is adding water to the ocean itself, the corners of the continent will also come down. So it's not just a matter of the ice melting away. You also have the corners that were warped up flattened down, okay? So you have two things that help sea level rise there. So here we go. Here's my isostasy recognition of the difference between oceanic crust. So as you can see, I got my glacier ice. You can see how the corners are pulled up. And once that ice melts off, the corners go back down. So again, two things, crustal rebound there, but both of these add to sea level rise. Some landform characteristics. Yes, you need to look at these. Structure refers to the nature, arrangement, and orientation of materials making up the landform. Process, the actions that have been combined to produce the landform, whether it was igneous, volcanic, sedimentary, whatever. Slope is the fundamental aspect of shape for any landform. Everything has a slope to it. Here in Oklahoma, our slope goes up to the west because we're headed for the Rocky Mountains. And you get out toward Black Mesa, that's the highest point in Oklahoma. Also a very interesting place, I should say, to visit if you ever get a chance. Drainage refers to the movement of water over and through the Earth's surface. So we have water that's toting the sediment around. And then the geographic inquiry into geomorphology is in the what, where, why, so what, how does it affect the Earth? So what is geomorphology? Geomorphology is the study of the landscape. That's as simple as it gets, the study of the landscape. All right, here are some critical concepts. Topography is the surface configuration of the Earth. Whether it's this up, down, rolling hills, it has topography. Right? The Earth is just not flat. Okay, we have a topography to it. A landform is an individual topographic feature. A mountain, Mount Elbert in Colorado. Okay. And then we have internal and external processes. So these you do need to know. Geomorphic processes. Internal, originate from within the earth, increase relief of the land surface. Increase through subduction and uplift, which means it builds mountains, okay, and hills. External, originate from sources above the lithosphere, such as the atmosphere or oceans, and decrease. So here are these important words you need to know here. And I'm going to underline this one right here. Denudation. That is the lowering of the landscape. And that is done through weathering, mass wasting, erosion, and so on. Okay? Building of the landscape is through extrusive, intrusive tectonism, folding and faulting. All right, so some more critical concepts here. Geologic time frame. How does it work? They actually have what we call golden spikes. Okay, so we have the first appearance of something and the last appearance of a specific creature or organism, species, whatever it is. Everybody knows about the time of the mammoths, when they were here, and all of a sudden meteorite comes and they're gone. So what we do is we look through our rock layers and we say, okay, I see this creature here, along with these other creatures. But then he's not here, and it disappeared. So we put a golden spike there. Boom. It was here, and then we go back to the first appearance, and it was here. And now we have a time block of when that creature lived. And then we go with the next creature. It was here, and then it was way up here. First appearance, last appearance. Now we have another time block. Some of these time blocks overlap and break down into your epochs and your periods and so on and so forth. It all depends on where they show up and when they are no longer seen. So, uniformitarianism. The present is the key to the past. What we see today has happened before. Past thinking believed that catastrophism or catastrophe shaped the landscape. And that's because we had dinosaurs. Everybody knew, hey, meteorite, boom, off the Yucatan Peninsula, took out the dinosaurs. And then people started looking at other things. Trilobites, 2 billion years old and disappeared. And then we've had other creatures come and go, the dodo bird, and so on and so forth. Right now, they're looking at a new time scale. So right now, we are in what we call the Holocene. That is when man first showed up. Okay, right here, the Holocene. Okay, and let me see if I can highlight that better. There we go, the Holocene. Okay, that's when man first appeared, around 10 to 12,000 years ago. Okay, and so now we're looking at these other things and these other time periods, but they're wanting to come up with a new time period because we've evolved to a point now where we started changing other things. So now they're looking at calling it the Anthropocene. So what is the Anthropocene or Anthropocene? Okay, so Anthropocene. Well, people have said, how about when we first tested the atom bomb? Or how about the Industrial Revolution? So anyway, people have thrown out these different target areas or target time zones and said we should rename this from the Anthropocene from here on up because we are different than our native man. So we've changed, we've evolved so much with technology and everything else. One of the things I've thrown out there is how about when we started messing up other terrestrial bodies such as the moon and Mars? Here's the issue. You really can't put a golden spike somewhere in that. Okay, because yes, we have evolved to where we're on other planets, but if you were looking at our planet to say, where's that time zone, where's that last appearance or first appearance, well, there's nowhere to put a golden spike. So this has been a huge debate of where would you put a spike at? How would you know? Because you can't just see this at one spot. This has to be across the world. Otherwise, I have to be able to see a last appearance and first appearance in different areas of the world. And that way it all correlates together. Well, there's no correlation right now for the Anthropocene, okay? Geologic time, vast periods of time over which geologic processes operate. Again, it's not in a blink of an eye. Maybe if we had some kind of catastrophe, we would see how a mountain is built if it just happened like that. But for the most part, these things happen very, very slowly. As far as your test goes, I'm going to tell you right now, there will be something associated with this top portion right here. So I would suggest that you familiarize yourself with that top portion. An example of scale 5 perspectives of the Horseshoe Park. I don't know necessarily why we threw scale back in here, but large scale, small scale, more detail, less detail. We've already seen this and we've already went over it. So again, less detail here. And then as you get down, we get more detail up here. So less detail here. Make this little circle there. And more detail here. Okay? Large cell, small. Major landform assemblages, flat plains, hills. We really don't need to really get into this too much. It just kind of shows you where all the mountains are, where the uplift has been, and so forth. And that's it for chapter 13. Hopefully this has been a good learning experience. Hopefully I'm getting the points across, and I look forward to seeing you on chapter 14. I will talk to you later. Bye.